I'm really jet lagged, so that means if I start to look as if I'm falling asleep, shout things, and in fact preemptively shout things at me during this talk to avoid that happening. I'm going to start by talking a bit about how we got to where we are with LLVM and the FreeBSD-based system, and then give a very quick overview of actually where we are, and then hopefully at the end talk a little bit about where we're planning on going and some of the opportunities that we have as a result of bringing in the stuff. So before I start making slides happening and waving my hands a lot, actually I've already started waving my hands a lot, so that's maybe not an ideal start. Who do we have in this audience? How many people here are FreeBSD developers? Okay, how many NetBSD developers? OpenBSD developers? People who wandered in off the streets and have no idea what they're doing? Okay, great. So I just want to start by having a quick overview of what is the toolchain, because I'm going to be talking about LLVM in the toolchain. Luba started a little bit talking about this, so obviously you think of the toolchain, the first thing that you interact with is the compiler, or the compiler driver in fact, which is either the GCC or Clang tool, which will drive all the other utilities, the compiler, the assembler, the linker. And there are some miscellaneous things like objdump, objcopy, NM, all of these little annoying tools that are really easy to write, but no one can be bothered. You can also sometimes think of the C and C++ standard libraries as being part of the toolchain. We often think of the C++ library as being part of the toolchain just because of historical reasons, that the GNU project developed it as part of GCC, and now LLVM has its own C++ standard library, libc++, which we now ship in FreeBSD 10. But basically the rule for what is in the toolchain is it's the stuff that you need to compile for the host platform when you're cross-compiling. So everything that you need to have available to run on your host when you're building code. And that sometimes includes the libraries that you'll be cross-compiling. So to go back in time now 7 years, the GNU project had this shiny new and exciting license, GPL v3. Prior to that, we had GCC and all of the binutil stuff, all of the GNU toolchain, and it had been under GPL v2, which no one really liked, but no one hated quite enough to rewrite it. That started to change with GPL v3. GPL v3 was an awesome thing for the GNU project to do for the BSD community. And we're very grateful to them for this, because it pushed a lot of companies to say, hang on a minute, there's this thing with a license that's not really annoying. We could use that instead. So we had a lot of downstream consumers of FreeBSD saying, GPL v2 we'll kind of tolerate, GPL v3 not allowed in the building. And because of that pushback from our consumers, we said no GPL v3 code allowed in the base system. And then we were kind of stuck, because GCC and binutils all went GPL v3, and we were stuck with old versions of them, and that was kind of a problem. So I guess I'm preaching to the choir here. How many people here have written GPL code? How many of you did it? Okay, everybody close your eyes so no one else will be blamed. And now put up your hands if you... seriously. So I guess most of you know this, but the reason we don't like the GPL is partly legal, because, well, it's complicated, but partly it's really complicated, you know? How many of you are lawyers? Okay. How many people talk to lawyers on a regular basis? How many of you keep your hand up if that makes you really happy? Okay, how many of you who didn't just have your hands up wish you could talk to lawyers more often? So the BSD license is really simple. You take the code, you don't pretend you wrote it, and you can do pretty much whatever you want. The GPL has some restrictions which probably are fine. For most of the stuff you want to do with GPL code, you can do it, and it's not a problem. Except that to be absolutely sure, you need to talk to a lawyer. And if you talk to a lawyer, they'll tell you it's fine. And you talk to another lawyer, they'll say, no, 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 don't do that. And you talk to a third lawyer, and he'll say, I have a completely unrelated opinion to the first two. But if you pay me more money, I'll have a different opinion. And that kind of scares people. And the answer that you eventually get when you've talked to enough lawyers is, actually, we have no idea what the GPL says, but we're hoping someone will be sued over it, and then there'll be some case law and some precedent, and then we'll know what happens. But in the BSD community, we sort of like the philosophy that the GNU project had, which was the motivation for the GPL, which was, we want people to engage with the community. But we think that the way they should do that is by saying, well, we need this stuff, and it's really expensive to maintain a fork, and if we open source it and we give it back to the community, then other people will develop it and they'll help us. And even though we hate that company over there, we have some common objectives, so we can work with them in this bit, and then we'll go back to suing them for totally unrelated things. And so this idea of voluntary participation in the community is really important for us. And it's one of the reasons that we're trying to minimize and eliminate the GPL code in the FreeBSD base system, that we should have companies and individuals engaging with the community, not because the license says you must do this, but because they've identified that it's in their best interest to do so. And that was a slightly longer digression than I intended, so sorry about that. But back on track, we're in 2007, and the GPL has this new edition, and now we're stuck with an old version of GCC, but there was some hope. There's this new thing, SVN commit message in the LLVM repository. Very brief initial check-in of C language parser. This is Chris Lattner, who's the head of the LLVM project and uses the username Saber, which makes me happy because I'm now not the person with the silliest username in any of these projects. Brand new C front end, and back then in 2007 when we were looking around for a new compiler, it could just about compile C code, and sometimes the C code it compiled worked. Sometimes it worked and did what you expected. Sometimes not so much. It could parse Objective-C, and that was nice. Couldn't generate code from it, but it could give you a pretty print of the AST. C++ support was completely missing, and it was written in C++, so this was kind of a problem because it couldn't self-host, and you can't replace your compiler with a compiler that can't build itself, because then you get a bit stuck the second time you try and build the base system. But it was definitely promising, and Apple was backing it, and after a little while Google and other people started contributing. So by 2009, Clang was a little bit more mature, and a couple of guys, Roman and Pavel, decided that they'd try and build FreeBSD using Clang. And it sort of worked. If you turned off optimizations, you could get a kernel that booted. And you know, optimizations, no one really needs compiler optimizations, right? So that was fine. And there were some bugs. So it turns out the kernel is actually one of the simpler bits of C code to compile. All of the really scary stuff in the kernel is in the assembly. If you start getting up to libc, that's when things get a bit crazy. So they opened a bug, which was a meta bug to track all of the other bugs that were blocking the FreeBSD build. And if you go and look for this bug, all of you people with laptops open now, you'll find that you have the little description of the bug and then the big list of all the other bugs that depended on. And time passed and more time passed, and about 18 months later the bug was closed. Well, no, sorry, 2 years later the bug was closed. 18 months later we could compile everything in the base system with Clang, but with some fairly invasive modifications to the source and some really ugly hacks to work around bugs, and occasionally compiling things at 0 because, well, there was a bug in an optimizer somewhere. And lots of people were getting involved with this. And eventually, May 2011, the bug that was tracking all of the things that were blocking the build on FreeBSD was closed, and it's awesome. May 2011 totally works. Base system builds on x86, and we're done, right? Yeah? I mean, there aren't any other architectures out there that anyone cares about, are there? And the base system is pretty much all the code in the world, so awesome. And then we switched and we shipped and we're done. Okay, maybe not. So it turns out we have this thing called the ports collection. And how many people here are ports committers? Any NetBSD package source people? Okay, keep your hand up if you're ports or, okay. Of you people, how many of you are really happy with the code in the ports that you maintain? Wow, what do you maintain? What? But it's written in PHP. You're happy with PHP code? Okay. That's slightly scary if you're happy with PHP code. I'm going to just stay on the other side of the room. You know, most of this code is written in a programming language, which might be something that looks a little bit like the programming language that is specified and has the same name. For example, many of them claim to be written in C, and they are written indeed in something that a C compiler will recognize. Sometimes this C compiler is a specific version of GCC. Often it is something that only a specific version of GCC will accept. When it gets to C++, however, that problem is magnified massively. So there are a few big issues there. There's, for example, the Sphinx project from CMU is a really nice speech recognition engine. And the last release was a couple of years ago, and it proudly announces that now it can build with GCC 4.4. something, and not earlier versions in the 4.4 series, and not later versions in the 4.4 series, but that one version of the compiler, because that version just happens to have the right set of bugs to accept their code. So yeah, a little bit scary. And all of this code, it's called ports because it's not written by FreeBSD developers, which means that we can't just put them all in a room and go around and beat them with a stick until they fix their code, which is very sad. So there are a few things that we needed to fix. One was, anyone remember POSIX 97? So that was a little while ago now. And they deprecated the CC utility because it accepted an undefined dialect of C. And back when POSIX 97 was specified, that was either KNRC or C89. Now it might be C99 or C11. Turns out if you call CC when it's GCC, it's the GNU 89 dialect. And that's a problem because C99 and C11 were very carefully designed so that any valid C89 program is also a valid C99 program, and every C99 program is also a valid C11 program. Unfortunately, there are certain keywords that are reserved for the implementation, and they start with double underscores. And GCC, when they extended C89, did not use these keywords when they were extending things, and so they added an inline keyword, which had some interesting semantics. And then C99 introduced an inline keyword, which had some different semantics. And the upshot of this is, if you compile GNU 89 code that uses the inline keyword in C99 mode, you get linker errors for multiply defined symbols. And Luba's nodding at the front for those who can't see him. He's probably had to fight this problem with various linkers. Most of these were really easy to fix. You just say, well, compile them as C99, but accept that the inline keyword does not mean what the developer thinks it means. Slightly more annoying problem was two-stage lookup in C++. How many people here use C++? you both have my commiserations. It turns out that in the C++ 98 specification, lookup of symbols in templates was a little bit confusing. And every single C++ compiler got it wrong. And just to make it more fun, every single C++ compiler got it wrong in a different way. That was a problem. In C++ 03, this was sort of clarified a bit, and various vendors sat down together and said, these are words. What do these words mean? And wrote some more words, and eventually agreed, and now GCC and Visual Studio can both do correct resolution and also have fallback code for their old, incorrect version. Clang only implemented the correct version and didn't have the fallback, although they're now adding Microsoft broken compatibility because it turns out most of the system headers on Windows rely on the broken version. Fortunately, this is a problem that doesn't affect FreeBSD because we don't need to compile Windows system headers on FreeBSD. But we do still have to deal with all the ports that think C++ is not the language that's defined by the C++ specification, it's the language that's defined by whatever G++ 4.3 accepts, or 4.4 accepts. And that's a little bit annoying. A lot of these actually are really simple to fix. You just explicitly qualify the symbol name with this and it works. Some things are a bit harder. The real problem with these is that when you get the error, you get as how many of you have tried compiling C++ code that's not quite right? Neither of the people who work with C++. Okay, great. So you always write bug-free code, the rest of you don't touch C++. But if you've seen anyone working on C++, you'll know you make a typo in a C++ file. And if you do this in a C file, you get an error saying parse error here. And if you do this in a C++ file, you get 10 pages of output saying template instantiation and then something that looks a bit like Lisp but with angle brackets instead of parentheses. Now that we have a C11 compiler in the base system, by the way, one of the things we started doing was actually using C11 features in the system headers, and Clang will allow you to accept C11 features as an extension even in C99 and C89 mode, so this is quite nice. And one of the things that C11 introduced was this generic qualifier which says it's designed for use in macros, and it's basically a switch statement but which switches on not the value of the expression but its type. And this is particularly useful for all of these things like isNaN and isinf and all the math.h and tgmath.h things that have to accept various different types. And the initial versions that we had of isNaN and isinf were implemented by saying if the size of the value is equal to the size of float, call the float version. If it's equal to the size of double, call the double version. If it's equal to the size of long double, call the long double version. And that was sort of okay, except it turns out size of float is equal to size of int on most platforms, and size of double is equal to size of long on most platforms. So you could pass an int to isNaN, and it would happily then do the implicit type conversion and turn it into a double precision value, which was obviously a number because, well, integers are numbers, that's kind of the definition. And then always return true. And if you're passing an integer to a function called is it infinity, or is it not a number, you're probably doing something wrong. A couple of ports actually were doing something wrong. More ports were just writing this as a quick way to test whether this function exists in their configure script. So they would say, what happens if I compile a small program that just is return isNaN brackets 1? And the thing would say compile error, because previously it was casting 1 to a float and then compiling it, calling the float version, and now it's saying, wait, int is not one of float double or long double, therefore you probably made a mistake. Mono was my favorite of these, which would test for the existence of isNaN with an int argument, and if it didn't exist, it would define an isnan with a double argument in its code. Most of these were fixed by just adding a .0 to the end of the macro, but it was slightly annoying. So as part of the import of all of the LLVM stuff, we've also imported the new LLVM libc++ library. This has the slightly annoying... oh, I've just stood on the thing that turns off the power supply. That's exciting. Slightly annoying side effect of this is that it's not ABI compatible with the GNU libsup C++. This would be more annoying if we were the only people suffering from this problem, but it turns out new versions of libsup C++ are also not ABI compatible with old versions, because implementing C++ 11 without changing the ABI is basically impossible. So lots of stuff needs recompiling, and as long as it compiles with Clang, it's fine. Since I wrote these slides, Baptiste has done a fair bit of work on making sure that GCC can now use libc++, and so this problem is probably going away, and we'll just use libc++ for everything. This gives us full support for C++ 11. I think the version we have in head now gives us full support for the C++ 1y, which will probably be C++ 14 draft specification. FreeBSD 10.1 will probably ship with C++ 14 support, assuming that C++ 14 is standardized before FreeBSD 10.1 is out. Although, to give you an idea of how using C++ delays releases for various projects, the C++ 11 specification was originally called C++ 0x. So even the standards committee is 2 years late delivering. One of the things we had to do to get libc++ ported was implement the full set of POSIX 2008 locale functions, so all of the things that implicitly take a locale in the C standard and in earlier versions of POSIX now have a version which has an _L suffix, which can take a locale object pointer. These include things like printf, so when you do a %d in printf, it may do thousands separators, or if you do a %f, it may use a comma or a full stop, depending on what your decimal point character is, depending on the locale. This is something many more people should be aware of, because it turns out lots of people use printf for things like writing comma-separated variable tables and don't realize that they're using the global locale, which may not be the C locale if your code isn't a library. And so this causes problems when a French person tries to use the code. And French people using code can cause all sorts of problems. But this particular problem is that now any number that has a decimal point in it is treated as being 2 columns in your CSV file. One of the issues that we had was that C++ 03 added some extra, not quite but nearly and basically standard stuff in the TR1 namespace. And libc++ was designed from the start as a C++ 11 library. So in the C++ 11 specification, all of this stuff was moved into the standard namespace and occasionally tweaked just a little bit for various reasons that people have discovered in the 8 years in between introducing this and people trying to use it. Mostly you can fix this code by just removing tr1::: from the declarations and by removing tr1/ from the include lines. But again, it's just something that lots of people had to go through and do in various ports, and it was slightly annoying. So the status as of FreeBSD 10, which we shipped a couple of months ago, is that Clang is the default and indeed the only installed system compiler for C and C++ on x86, both 32-bit and 64-bit, and on ARM v6. For those of you who are not FreeBSD people, ARM v6 is what we call ARM v7 plus Raspberry Pi. It requires various features of the later ARM v6 revisions right up to the stuff that is included in the ARM 1156 chip that is in the Raspberry Pi. So it doesn't actually support all ARMv6 architectures because they had some quite annoying limitations. And the Raspberry Pi, by the way, really annoys people at ARM because a couple of years ago they were just about to say ARMv7 is the earliest thing we support in software. If you want to use something embedded, go for the Cortex-M line. If you want to use something for higher performance stuff, the Cortex-A line. It's all ARMv7 or ARMv7M, and we don't need to deal with all of that old stuff anymore. And then the Raspberry Pi came out with its ARM11 chip, which is an ARMv6, and they started to cry. So if you're in Cambridge, have some beers with the ARM people, and they will complain a lot about this. It's very fun. Unfortunately, it's also a problem for us because we would also quite like to be able to have just ARMv7 or later support in FreeBSD, but ARMv6 is still around. And Marvel is still shipping some ARMv5 chips, but we try not to listen to them. But that's two architectures, and FreeBSD supports several architectures beyond that, so there's a little bit of work there. In terms of standards compliance, we still have a few math functions from C99 missing, and the various people on the FreeBSD numerics list, whenever I bring this up, say, yes, I have a version, but it's not quite perfect, so I won't commit it. But I will have it perfect soon. And they've been saying this for about 2 years now, so hopefully it's getting asymptotically closer to perfect, and will eventually there'll be a rounding error and they'll think it's perfect. That's usually what happens with the floating point stuff. C++11 and C11 is basically there. We have mostly full support for both. There are a few little limitations. Thread local is a new keyword in C++11 because they like just reusing identifiers for new keywords in C++ because no one has any legacy C++ code, so it's totally fine. Thread local is really exciting in C++ because any C++ value can have constructors and destructors, which are code that runs when the value is created and destroyed. And if you have one in a global, then they must run when either the program starts and exits or the library is loaded and unloaded. If you have one in a scoped static, it must run in a thread-safe way the first time that variable comes into scope, which you can use for lazy initialization, which is kind of nice, but is a little bit scary to implement. But if it's a value in thread local storage, it must be created every time a thread is created and destroyed every time a thread is destroyed. And so this needs a little bit of support code somewhere, and it needs a group of us to agree on what the ABI for this should be, because we don't want to do it differently from Linux and OS X, and so far, as far as I can tell, everyone is waiting for someone else to do it first so we can learn from their mistakes. One of the things that's still on the to-do list is OpenMP. The most important things to use OpenMP on FreeBSD are Phoronix benchmarks, because one thing you'll see if you look at any of these is many pages of results, mostly showing FreeBSD is faster, or LLVM is faster than GCC, or sometimes the other way around, but not much in it, usually 5–10%. And then one which is showing, and GCC is 8 times faster than LLVM, because that's the one that uses OpenMP. And then in the last page, normalized results. And so that one outlier really nudges everything down and makes LLVM look really slow, and by extension, if they're comparing FreeBSD to Ubuntu, which is something they like doing, then it makes FreeBSD look slow because they're using the system compiler on both, and for us it's a compiler that doesn't support OpenMP. And Clang doesn't yet, but the patches from Intel are available. Last week, in fact, Alptoka, who by the way has an awesome name, ported the Intel OpenMP runtime, which was released a few months ago under a MIT license and UUIC license, to FreeBSD. Everything except the CPU affinity code works, and the CPU affinity code is now a bit more modular, so it's easy to add. this will be imported into the base system at some point and will be imported into ports sooner. The patches for Clang are currently being upstreamed, so what our strategy is likely to be there is to import Intel's fork of Clang, which has all the OpenMP support, into ports, use that for the ports that need OpenMP, and then when these patches are upstreamed, which should hopefully be before LLVM 3.5, we'll import the new version of LLVM, get rid of the port of the fork, and just use that. A lot of the work that's been done in the ports tree has been to separate out the specific reasons why ports can't build with Clang. So rather than saying this port needs GCC, they'll say this port needs OpenMP. So that means it's very easy for us to just flip a switch somewhere in the ports tree and say, now everything that needs OpenMP, build it with this compiler, and then this compiler, and then eventually we should have it all working. And then there's Itanium. How many people here use Itanium? Are you trying to put your hand up, or are you just embarrassed about using Itanium? It's okay, we've all made mistakes. Yeah, so last time I gave a talk on this subject, I had both Itanium users in the room, but this time I don't think I do have either of them. So Itanium is a problem. Spark 64 now builds with Clang. And building with Clang, right? That's all we need. We don't need it to work. Yeah, okay, maybe we do. But we're getting there. PowerPC 64 works without optimizations, which means now we're not missing features, we're just having to fix some bugs. And a couple of people at the Argonne National Laboratory in the US are very enthusiastic about using Clang on their very, very expensive computers that are all PowerPC 64, so they're quite aggressively chasing bugs there. PowerPC 32, I think, is still missing support for thread local storage and one kind of relocation. I don't remember which one. So again, that's just, if anyone cares about PowerPC 32, it's probably about a week's work to get it up to the same state as PowerPC 64. Are there any semi-half people here? You ship products based on PowerPC 32. You should care about this. MIPS is ongoing. The MIPS people are making very rapid progress, much of it in a forwards direction. Last week they did manage to commit something that broke every single function call when compiled without optimization, which was quite special, but they've now fixed that. Yeah, I don't know if there will be any Itanium users by the time FreeBSD 11 is out, but one possible way of fixing it is external toolchain support, and that's something that is sort of mostly working, and Brooks has worked on that, and I think probably Ed will do a bit more work on it soon. We really want to kill GCC 4.2.1 in the in-tree builds because it's just old and crufty and horrible, and it would be quite nice if we could build the base system with a modern GCC, partly just so we have a baseline to say, well, hang on, Clang is slower here. Clang people, fix these performance bugs. Partly because you can easily identify a compiler bug if you can say, builds correctly with this compiler, doesn't build correctly with this compiler. Increasingly, we're actually wanting to use features of C11, and the C++ stack now basically requires a C++11 compiler. The next version of Clang will require a C++11 compiler, so being stuck with a C++98 compiler on some architectures is a problem. Unfortunately, if we have an external toolchain and we don't have an LLVM port for an architecture, then that means we will miss out on other features. And what are these other features? I would hear you say if any of you were still awake. Who's still awake? Okay, just George. So when people compare Clang and GCC, they're sort of missing the point, because GCC is a compiler. And it's a pretty good compiler. I mean, I like to mock GCC for many, many reasons. But it's served the project well. We've been using it for, what, 30 years? It still works. It's still very competitive in terms of performance. It supports a load of architectures. It does a pretty reasonable job of being a compiler. LLVM is not a compiler. LLVM is a set of libraries for building a compiler, and Clang is just a thing that uses these libraries to implement the C and C++ compiler, and that's probably the most visible part of Clang. But if you look at why Apple started backing LLVM in the first place, it wasn't because they wanted a replacement for GCC. It was because they wanted a replacement for their in-house OpenGL shader language compiler. And they had a JIT for 32-bit PowerPC and a JIT for 32-bit x86, and nothing for 64-bit PowerPC and nothing for 64-bit x86. And both of these were handwritten, and they had different bugs, and so porting code between them was a bit horrible. And they also had an interpreter, and the interpreter shared no code with the compiler. So if you wanted to write something that used shaders on OS X, then testing was very exciting. When they switched to using LLVM, they had one thing that would just turn the GLSL built-in things into calls to functions, and those functions were the functions that were implemented in their interpreter. And then they just linked the whole thing together, and they ran link time optimizations and inlined all of those functions, and then they got machine code out. And that's a really simple and nice and fast way of writing a JIT compiler if you already have an interpreter. You just statically do each of the interpreter steps by saying, when you get to this bytecode, call this function which implements this bytecode. When you get to this bytecode, do the same for this, and then just rely on the inliner to source it all out. And this actually works very well, and I think Apple got something like 30% speed up over their handwritten JIT when they did this, and they got PowerPC 64 support and x86 64 support for free. And then they had one implementation of each of these functions rather than 4. So lots of advantages. And there are lots of things that we'd like to do with LLVM. One thing that we've talked a little bit about with various ports people is install time optimization. So LLVM IR is not like Java bytecode. It's not designed to be processor agnostic, and it's really hard to do that with C anyway, because by the time you've run the C preprocessor, even not the compiler, you no longer have target independent code. You have various things that rely on the if-def big endian or if-def little endian, that sort of thing. Various built-ins that tell you what the word size is. All of these things mean that you'll get different C code fed to the C compiler depending on what the built-in macros that the compiler defines are. So that's not a goal. It would sort of be nice to be able to use the portable native client stuff for some things, so you could have architecture agnostic binaries, but that's not a high priority. However, even though it's not architecture agnostic, it is microarchitecture agnostic. So various processors have different sequences of instructions that are fast, and different branch predictor behaviors, different cache sizes, all of these things which the LLVM backend knows about and can use when it's instruction scheduling. So one example that was a GCC bug or performance bug about 10 years ago, they used to always extend sequences of multiply by a constant to a series of adds and shifts, because in the Pentium and every earlier x86 chip that would be faster. But on the AMD Athlon, when it came out, the multiplier was really fast, and there were 2 of them. And so if you had 2 multiplies, they could be in separate pipelines and it would all be nice and fast. But if you use the adds and the shifts, then you introduce data dependencies on this 3 to 7 instruction sequence, and each one of those has to go all the way through the pipeline and then back to the start. And so it was much slower. And so the simple transform, which was a big speed up on the Pentium, was a big slowdown on the Athlon. And if you want to have code that's fast on both, then you need to compile very subtly differently for each one. So it would be really nice if the packages could ship with the x86 generic LLVM and then when you do the install, you then say, and for this particular machine I have exactly this model of processor, please give me the optimized binary. One of the things we can do now we have, and one of the nice things about a BSD system is it's an integrated system, so you have complete control over the compiler, the runtime linker, the packaging system, all of these things, and so there's a possibility to do very tight integration. And so traditionally, very traditionally, optimization stops on compilation unit boundaries, and more recently it stops on shared library boundaries. But it would be really nice if we could say, well, every time you install a shared library, also install the LLVM for that library. And then if you have only one program that's using that shared library, well, just link them together and do the link time optimization. If you have multiple versions, then maybe you want to pull out some things from the shared library and inline those, but still use the shared library. And I wrote a pass a few years ago which does this and finds all the things in the shared library that are safe to pull out and inline in other programs. And this is really common for C++ code because you have little tiny accessor methods which have to be private so that you preserve ABIs, but are just return the value at this offset. And the difficulty is, in the general case, well, you need to invalidate those every time you recompile the library. But if we are installing the library from the packages and installing the binary from the packages, then we can install the specialized version and the unspecialized version. We can do the optimization on the specialized version, and then if you upgrade the library, then we say, well, just now fall back to using the unspecialized version until we've done this process again. How many of you have worked on ARM stuff recently? Okay. How many of you have heard of Big Little? Okay, so this is a new thing from ARM where you have some fast cores and some slow cores. And the idea was that you would have some programs that were very CPU dependent, you'd run them on the fast cores, and other ones that weren't, you'd run them on the slow cores, and you get really good power efficiency. And then they actually tried it. And it turns out you have some phases of some programs which are very CPU dependent and you want to run those on the fast cores. And you have other phases which are not and you want to run those on the slow cores. And switching between them and working out when this happens just is not very easy. So the new ARM v8 designs have lots and lots of performance counters to enable operating systems, schedulers, to make good decisions about when various things should run. And, well, now we're doing very detailed performance analysis of code as it runs. Wouldn't it be nice to take that information and put it back into your compiler and use this for feedback-driven optimization? And this is something that JVMs have done for a long time, and the .NET CLR does. And SGI had a project in the 90s called Dynamo, which did this with a MIPS on MIPS emulator. So you'd run MIPS code on a MIPS processor, but in a MIPS emulator. It would do the profiling, and it would then transform the code and then run it as native code, and you get about a 10% speed up. And if you're doing big server type things where you have 100% CPU utilization all the time, then actually this would be quite a nice thing to have. I've mostly talked about the compiler and the fun things we can do there. There are other bits of the toolchain. The assembler is pretty easy to replace because LLVM has a built-in assembler, and if you use Clang with -integrated-as, you use that. And I think it's now the default on all the platforms where Clang is CC. So the only thing that we need for an AS command is a little tiny wrapper that says, read this text file, pass it to this library. I really should just write that. I just haven't got around to it. There are things like LLVM obj dump. The only reason we haven't switched to LLVM obj dump so far is that the code that allows it to find the line numbers from the debug information was only just added to the LLVM libraries. And people who run obj dump a lot, which basically means Robert, really like being able to find what the C code that corresponds to their binary dump is. The GNU debugger we have in the base system is completely useless because recent versions of Clang and recent versions of GCC emit debug information in version 4 of the dwarf standard, and the really ancient version of GDB that we have only understands version 2. So if you actually want to debug stuff on FreeBSD, you probably are installing GDB from ports now. LDB, which is the LLVM debugger, also understands dwarf 4 and has some quite nice features. It's also a set of libraries, so it's easy to integrate in IDEs and things. And it's in head now. We'll probably ship it in 10.1, but as an optional thing, and by 11 it should be the default debugger. Just one final thing, and I realize I'm slightly over time, so sorry about that. Gosh, am I keeping you people from coffee? Sorry, that's a terrifying thought. There are lots of little compilers in FreeBSD that are not things you think of as compilers. So there's a JIT for BPF, and I don't know how many firewalls we have in FreeBSD now. Kirk probably knows. George, how many firewalls do we have in FreeBSD? So between 2 and 4, and there's also BPF for packet filtering, which isn't a firewall but does the same. You write a little program for it and it runs it on every packet, and so for some architectures we have a BPF JIT. I actually wrote a little proof of concept that you took BPF bytecodes, fed them into LLVM, and it generated about 1 x86 instruction per BPF bytecode on average. And the handwritten JIT we have in the kernel averages about 10 instructions, so probably you'll see a little bit of speed up there. But the question is, how would we integrate this? And one approach is we could take LLVM and we could run it in the kernel, and I'm sure all the kernel hackers in the room, how many are you here? I'm sure you're all overjoyed at the thought of having 5 megabytes of C++ code that doesn't handle out-of-memory conditions well running in the kernel. Yeah, great idea. Okay, maybe not that one then. So one approach is to run it in user space and have a device which will push up the firewall rules as bytecodes to a device, do the compilation in user space, and then push the code back in. But also, Luigi is giving a talk this afternoon about NetMap. NetMap is kind of exciting. It lets you do much of what the network stack needs to do in user space, and it does it very fast. And so with that, we could take IPFW, which he already has running in user space. We could do the JIT compilation of complex firewall rules in user space, where if it crashes, well, just restart the process. And then have very fast, very specialized firewall rules, JIT compiled for your native target, running in an environment where they can do lots of threading things and not have to worry about the resource constraints of the kernel. And we get this then for free on every architecture that LLVM supports. And I hear there's a company that uses FreeBSD that quite likes doing network processing on MIPS, for example. And with that, I will stop speaking and let you drink coffee. Oh no, someone's going to stop you drinking coffee and ask a question. Yes. I've been moaning at Google people for about a year about their complete lack of understanding of how to write platform abstraction layers, and it turns out they were actually listening. So the new versions of the sanitizers have, sorry, the question for anyone who couldn't hear it was, do we plan on porting the various sanitizers? And Clang has a set of these things, memory sanitizer and address sanitizer and thread sanitizer and other things, which are compile time instrumentation, which then do runtime checks of various things. So, for example, the undefined behavior sanitizer, anything that might be undefined behavior, it will insert a check saying, is this undefined behavior? If so, call a trap handler. The address sanitizer and memory sanitizers check for various memory errors. The thread sanitizer checks for data races. All of these need a little bit of runtime code. Some of it is very easy to port and actually just works out of the box on FreeBSD, but without the nice error reporting. We need to plug in some code that will do the stack printing a bit more nicely, but that's not very complicated. The code for doing that is in the base system. We just need to wire it up. The more complicated things are address sanitizer and memory sanitizer, and they need to hook into bits of libc. One of the things we'd like to do actually is have libc itself use address sanitizer and memory sanitizer, and it's not designed for that at all because it assumes that libc is this opaque binary blob and you can interpose between it. But they've now really cleaned up the layering of how they do the interposition. And Roman and someone else are currently working on the port. They have some patches, but I don't know how stable they are. But I would really like it if FreeBSD 11 shipped with all of the sanitizers out of the box. And I think we're probably on target to get that. So, does anyone else want to keep people from coffee? No brave souls? Okay. Run away. This, by the way, is how I feel.